Okay, so I have already written out this first problem just so that way this video doesn't get super long because I want to do a couple of problems. And so we're going to go over resistance. And resistance in physics is looked at as like when current is moving through a wire, right? We have moving charges. So we have our electrons moving, and they don't just have empty space that they're moving through. They're going to be running into other subatomic particles. At least that's what the current story is right now in physics, and I guess has been for quite a while. So it's just like if you were in a hallway and there were a whole bunch of people in the hallway, you're going to have a lot of resistance. You're going to maybe bump into some people, they'll slow you down. That's sort of how I look at this resistance. So in this question, we're asked, can a 2.2 millimeter diameter copper wire have the same resistance as a tungsten wire of the same length? So I also use this method. It's called the GUESS method. And it's where I write down GUESS, and we'll go over what those mean. But those kind of help me to lay out what I have and to help me organize my thoughts on the paper, which is really, really important when you're doing a physics problem. Okay, so what we're doing here is we're given that, and for our G's, we are given, it's right here, we are given that our diameter of our copper wire is 2.2 millimeters. We're also given that the area, the cross-sectional area, because of a wire, it's going to be like this, right? So that is just the cross-sectional area of a circle. And so the area of a circle is pi r squared. That is also equal to pi d divided by 2 squared, which is equal to pi d squared divided by 4. And what I did right there was I just squared this 2 and then took that out, made it a 4. Okay, and so what we want to know is what diameter of tungsten to a diameter of copper will yield the same resistance. So since these are going to be the same length, right? We have the same length. That means that the only way to get more or less of the tungsten to equal what we want it to equal, the same resistance of the copper wire, is going to be based on the diameter. So we're going to write here our equations. So we have our givens, our unknowns, and now our equations. And so we write down just the regular equation for resistance, which is right here. Now resistance is equal to resistivity times length divided by area. And this resistivity is something that is particular for each material. There are values for each material, so it's material dependent. Okay, so we have the resistance of copper equals, I'm just going to write Cu, that means copper, is equal to the resistivity of copper times the length divided by the area. And then I did what I did up here. I just went ahead and I substituted in the area, which is the pi d squared divided by 4, and then dividing is the same thing as multiplying by the reciprocal. So I just went ahead and I multiplied that by the reciprocal, and that's what this gave me, that the resistance of copper is equal to the resistivity of copper times the length times 4 divided by pi d squared. Now the resistance of tungsten is going to be the exact same equation because it is also a wire with some cross-sectional area. Okay, and so we have right here, the lengths, remember, are the same, so they don't need a subscript. So we just have the resistance of tungsten is equal to the resistivity of tungsten times the length times 4 divided by pi d squared. Now we have S. So we are going to substitute in some values that we had up here in our equation. So I like to solve symbolically first. I found in physics that is the way to go. So we have up here the two equations, and we're going to set them equal to each other because we want for them to be equal. So we have the resistivity of tungsten times the length times 4 divided by pi d squared is equal to the resistivity of copper times the length times 4 divided by pi d squared. you cancel all of the equal values, right? So those are all just going to cancel. And you're left with the resistivity of tungsten. This is what you're left with. The resistivity of tungsten divided by the diameter of tungsten squared equals the resistivity of copper divided by the diameter of copper squared. And then I take the inverse of that, which just means you're going to flip them. Flip them over. And so now you have this right here, which is the diameter of tungsten squared divided by the resistivity of tungsten equals what we have over here, the diameter of copper squared divided by the resistivity of copper. We are going to isolate the diameter because that's what we're looking for. Remember, we want to know what diameter is going to yield this equal resistance. And so we go ahead and we isolate by multiplying both sides times the resistivity of tungsten, and we are left with dt squared. So we're going to have to take the square root of that so that way we can get just regular old diameter of tungsten. And so we take the square root, and then what I did was, if you look at this d squared, well, the square root of d squared is just d. So I went ahead and I pulled d out front. So the diameter of tungsten equals the diameter of copper times the square root of the resistivity of tungsten times divided by the resistivity of copper. And then we just plug in our values. And up here, and on a test, you would probably be given these resistivities. Like I said, they're material dependent. If not, they're usually in a textbook. But for homework, you'll probably have to look them up. This was a question in the back of the book, and so I had to look up the resistivities. But for time's sake, I just put them in. So then we have our final S, which is to solve. So we're going to plug everything in here. And we have the diameter of tungsten is equal to the diameter of the copper, which remember was 2.2 millimeters, which is the same as 2.2 times 10 to the negative 3 meters, times the square root of the resistivity of tungsten, which is 5.6 times 10 to the negative 8 ohm meters. I know that looks like an R, but I kind of remember that it looks like an R and it stands for the resistivity. Anyways, 5.6 times 10 to the negative 8 ohm meters, and then divided by the resistivity of copper, which is the 1.68 times 10 to the negative 8 ohm meters, and that gives us 0.00401. And just to recap, in order to get that into scientific notation, we move it 1, 2, 3 times, and so that's going to give us 4.01 times 10 to the negative 3 meters is the diameter of tungsten needed to equal the resistance, not resistivity. I like that word resistivity, I think, because I use it in place of resistance, but that's not what that's supposed to be. That's supposed to be the resistance of a 2.2 millimeter copper wire of the same length. Okay, now I went through that super fast. I hope I didn't go too fast, but since this is a video, you can always pause it and go back. So hopefully it was still helpful. Okay, so now we have this one, which is going to take, I'm going to be writing, so it'll take a little bit more time. So now we're going to calculate the ratio of the resistance of a 10 meters of aluminum 2.2. Did I write that right? That sounds funny. Calculate the ratio of the resistance of 10 meters of aluminum wire, 2.2 meters in diameter, to 24 meters of copper wire, 1.8 millimeters in diameter. Okay, so the first thing we're going to do is write down what we're given. Okay, so this is going to be a much more, it'll be a slower step, so you'll be able to see if you want to know how to do the guess method and apply it to your physics problems. So what we're given is that we are given, let's see, calculate the ratio of the resistance of, so we have 10 meters of aluminum wire, and so that's going to be the length of our aluminum wire. So length, aluminum. Okay, we'll just have a little subscript so we know what it is. Then we also know that 2.2 millimeters of aluminum that's going to be the diameter of our aluminum. Okay, and then we also have 24 meters of copper. So let me do this. Okay, and that is 1.8 millimeters. So that's the diameter of our copper. And we can also go ahead and just change these to make them easier to plug them in when we need them, if that helps you. So we'll go ahead and put those in the correct notation, because remember, in physics we always want to use kilograms, meters, and seconds. So just a good reminder. Okay, now what are our unknowns? Well, we want to know the ratio of resistance of aluminum to the resistance of copper. Okay, well that tells us we're going to need to know the resistance of aluminum and the resistance of copper. And that's cool because we have an equation to do that. So the resistance of anything here is going to be the resistivity, which is material dependent, times the length divided by the cross-sectional area. Well, again, we're talking about wires here, so that means that our area, our area is going to be that of a circle. So we can also put that in our givens because it's a given, right? Pi r squared equals our area. That also equals pi d divided by 2 squared, which also equals pi d squared over 4. Okay, so our equations are going to be the same. They'll have different values, but it'll be the same equation. So we'll do P copper, L copper, divided by area. Okay. Well, I guess these will be different too. So now we can substitute in and go ahead and calculate the resistance first for our aluminum. So the resistivity of aluminum is 2.65 times 10 to the negative 8 ohm meters times the length of our aluminum, which is up here. So we have 10 meters divided by the area, which, oh, I didn't show that up here. So when I'm doing the resistance, I like to do it like this. Resistivity times length divided by area. Well, I like to, instead of, I guess I'll just show it like I did in the front, but be pi d squared divided by 4. Well, that's the same as multiplying by the reciprocal of that. So that equals resistivity times length times pi d squared 4. So I'm going to do that up here. I'm going to apply that here. So we have here, we have resistivity, resistivity, length, and then there's the 4. Then next we're going to have pi times the diameter of the aluminum, which we have is 2.2 times 10 to the negative 3 meters. Don't forget to square that. Okay, and then we also have the resistivity, excuse me, I told you I like that word, the resistance of the copper, which is equal to the resistivity of copper, which is 1.68 times 10 to the negative 8 ohm meters times the length which is, where'd it go? Here we go. No, that's diameter, 24 meters times 4 divided by pi, and then the diameter, which is going to be 1.8 times 10 to the negative 3 meters. Don't forget to square it. And then we'll go ahead and we will put these in the calculator real quick. Grab my calculator. Okay. Just got a really big number, and I realized I didn't put in my times 10 to the negative 8, so try again. Okay. So for the resistance for the aluminum, we have 0.069712. It goes on and on. 49. And that'll be ohms. So what we want here is we'll do 1, 2. That's a negative 2 ohms. Okay. And then now we'll go ahead and compute for the copper. Okay, and so and you really could keep them in the decimals for this because we're doing the ratio, but there we go. Oh, that's ohms. Sorry, I ran out of room there. It's a little bit sloppy. Okay, so now what we need to do is we have the two resistances, and we want to know, remember, we want to know the resistance of aluminum to the resistance of copper. So we'll go ahead and we'll use the decimals. 0.06971249 divided by 0.158447. Use whatever, that's fine. It's a few more extra decimals, doesn't hurt. You don't want to use rounded numbers if you can help it. Okay, and then I get that the ratio of our resistances is 0.4399. Let's see, they gave us 2 decimal places, so that's what we'll use for our sig figs. So 0.44 is the ratio of our resistances. Okay, and 0.44 doesn't have, it's just the ratio. So you could say 0.44 ohms, I guess, because these are ohms, but technically the ohms would cancel because dividing by them, so just be 0.44, it's just a ratio. Okay, and then, let me see, I don't want the video to get too long. There's another, this is a pretty big one too. Okay, okay, so we have has a resistance of 15 ohms at what point along its length must the wire be cut? So that the resistance of one piece is 4.0 times the resistance of the other. And then what is the resistance of each piece? Okay, so certain copper wire has a resistance of 15 ohms. At what point along its length must the wire be cut so that the resistance of one piece is 4 times the resistance of the other? And what is the resistance of each piece? Okay, so let's write down our givens. So we know that the resistance of the copper wire is 15 ohms. And then it wants to know what point along its length must the wire be cut so that the resistance of one piece, so this whole thing is the copper, so we're going to have resistance 1, resistance 2 equals our resistance. So it says the wire must be cut so that the resistance of one piece is 4 times the resistance of the other. So R2 is just going to be 4 times that of R1. Okay, does that make sense? Because, let's see, at what point along its length must the wire be cut? Yeah. Okay, and so then we want to know what is the resistance of each piece. Okay. So our unknown is the resistance of the pieces, which I tell you what, let's draw a picture because that's really helpful. So if we have a wire, we have a copper wire. Well, let's do it in orange because copper is kind of orange. Let's do this color. Okay, so we have a copper wire and it's more brown, but you know. Okay, what point along its length must the wire be cut? So we're going to cut the wire. So the resistance of one piece is 4 times the resistance of the other. Okay, so we're going to have, this is going to be L1, this will be L2, and this whole thing is L. Okay? And so, if we want to know the resistance of each piece, then what we will do is, actually, let's go ahead and let's do the first question first, which says at what point along the length must it be cut? So we know that, let's finish up our unknowns. This is why I like the guess method, because you see you can kind of get lost in the question if you don't stay on track. So our unknowns is our resistance and the length at which the wire must be cut. To equal 4 times R1. Okay. And then our equations, well, we have our equation for resistance, which is the resistivity times the length divided by the area. And again, we're dealing with a wire here, so our area is equal to pi r squared, which is equal to pi d divided by 2 squared, which is equal to pi d squared divided by 4. Okay, so we know that, since resistance equals the resistivity times the length times the area, and we're told that R equals R1 plus R2, and we know that R equals R1 plus 4R1 because we have right here, remember we said that R2 equals 4R1. So we just plug that in right there. We can rewrite this in terms of L. Okay? Because that's what we're looking for. We're looking for the length at which this must be cut. So we will use this equation and we'll say the resistivity times L divided by A equals the resistivity L1 divided by A plus resistivity, we'll just say 4 times because it's going to be 4 times the resistivity, L1 divided by A. Okay, so then we're going to have all of our like things are going to cancel. So it's just going to be, because our resistivities are the same. It's still the copper wire. Our area is still the same. Our cross-sectional area is still the same. So the only thing that's changing is this 4L1. So then we have these cancel and this cancels. And then we have L equals, let me go back to red. L equals L1 plus 4L1, and that equals, let's not do it like that. I used to get confused in class because my teacher kept going equals, equals, equals. I'm like, whoa, 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 what's with all the equals? Okay, so we'll do it right here. Equals 5L1. So what this means is that the total length, the total L of the wire is 5 times that of L1. Because remember, when you have multiplication, it says 5. Multiplication, another thing you can say is of, right? 5 of L, like of. So that's another way of talking about multiplication. So the total length of the wire is 5 times that of L1. And so what you can also look at is if you divide this by 5, you could have L1 equals, and we're doing this right here and this, right? Well, let me make it clearer. So we have L equals 5L1. Well, so if I want to know what L1 is, I have L divided by 5 equals L1. So what this tells us is that L1 is 1/5 or 20% of L. So the short wire is 20% of the total length of the wire. Okay, So that's what that tells us. But we're not done yet. We still need to calculate the resistance of each piece, which should be very easy now. So it has a total length, remember, of L, but it's broken into these two pieces. And we know that the resistance of the second portion, this one, is 4 times that of this one. That's what the question tells us, right? It says at what point along its length must the wire be cut so that the resistance of one piece is 4 times? So that's what we're looking for when we're looking at this resistance. This one is resistance 1, and this is 4 times resistance 1. So we could do guess again. We could write down that resistance 1 equals just, I can say resistance equals 4R1. This is for the second portion. And then resistance for the first portion equals R1. So this is for this, and this is this. Okay. And then we know that the total, well, let's do what are unknowns. We know our unknown is the total resistance. Resistance of each piece. And then our equations are going to be these that we put up here, and that R1 plus R2 equals, and we're told that the total resistance is 15 ohms. So it has a resistance of 15 ohms. So that's our total. And we want to know what each piece will be. So we're going to substitute for R2 like we did to make that 4R1 in its place. And what we'll do is we'll put R1 plus 4R1 equals R. Okay, so then we have 5R1 equals R. And we end up with, remember our resistance we have is 15 ohms. So 5R1 equals 15 ohms. And then we can divide both sides by 5, and we get that R1 is going to be 3 ohms. So we know that R1 is 3 ohms. And since we know that the resistance of part 2 is going to be 4 times that, so remember R2 is 4 times R1. So we know that it's going to be 4 times 3 ohms, which is going to equal 12 ohms. Pretty cool. So there we go. So then we have, I think that's all we need to know is each piece, right? So the first piece, R1, is 3 ohms. R2 is 12 ohms. Another way you could do that was we were given the total is 15. And so you could say 15 minus 3. That would also be 12. So there you go. I hope that you found this helpful. And just keep at it, guys. Keep at it.